So, how to start? I'm a researcher at Stockholm University, and basically I'm an astroparticle physicist, so I study, let's say, the very, very big objects through very small particles. And the big question I'm facing like every day is what is the universe made of? And of course, the answer is a lot of stuff, obviously. We have planets, we have stars, we have galaxies, but we have also pretty strong evidence that that's not the whole story. We heard today about the CMB, so, okay. And I guess that everyone at this point knows pretty much what's going on in here. And the point is that this pattern is almost impossible to interpret if we don't make up the hypothesis that, let's say, roughly 15 to 20% of the total matter of the universe is of what made us, like baryons, electrons, neutrinos, and the remaining part is of an unknown type. An unknown type which is invisible, is weakly interacting, and yeah, so basically it's just an assumption that we make in order to make sense of the tensions in what we can see and what we actually know. We heard of the dark matter term here a lot, except the fact that, yeah, basically we have no idea what dark matter is. So we do have hypotheses, and our goal as astroparticle physicists is to test those hypotheses, to build experiments that try to detect this matter, so detect the particles that make up dark matter in a controlled environment in a lab. So as I said, we do have hypotheses, and hypotheses are needed in order to make an experiment, and one of these hypotheses involves the so-called axions. Axions are particles that are actually named after a detergent. Yeah, because they were firstly introduced to clear up a problem that was unrelated to dark matter. Actually, it was a problem of fundamental physics, totally unrelated. And just to explain, I mean, it's very technical. It involves the way like the nuclear forces behave if we flip the direction of time. But a very quick way, and I think a clear way of introducing this problem is to look at the electric dipole moment of the neutron. Because the theory predicts the neutron to have a certain dipole moment, electric dipole moment, which is a function of a certain parameter theta. Now, if we look at all the theory, theta is an angle. So basically, it is expected to vary between 0 and 2 pi. But the problem is, as far as we can measure, this theta is constrained to be smaller than 10 to the minus 10. So it's basically 0. Right? As far as we can measure, theta is 0. So theoretical physicists try to explain this by saying, okay, this is a weird parameter, so that's not actually a parameter. There's a dynamic, this is a dynamic quantity. So it is 0 because it evolves to 0 during like the evolution of the universe from like the Big Bang to the early stage of cosmology. And what happens is that if you do that, you end up with residual degrees of freedom oscillation in some fields. Those are the axions. And so axions are expected to be this particle that solve this theoretical problem, but also can explain dark matter for free. So they are a pretty good candidate, and we are looking forward to detect them. How we can do that? We can use the theory that predicts the axion to be coupled with electromagnetic particle, with photons. So we can say the theory predicts that the axion can decay into 2 photons, with the probability of this process being proportional to some coupling constant g, which is small, of course. And in fact, it is so small that this process is very unlikely. When I mean unlikely, I mean the fact that the lifetime of an axion is expected to be 1 million of times the age of the universe, if you are lucky. So there's no way we can detect axions through this. But we can do a little trick here with the magic of Feynman diagrams and study this process. So what are we seeing here? We are saying we are not interested in getting 2 photons from an axion, but instead we are saying we are giving a photon to an axion, and we are hoping to convert this axion into a photon, into another photon. This means, in a classical way, we pump a very strong magnetic field, a magnetic field that has a lot of virtual photons, and we hope to get an electric field given by the axion. This is small, of course, so we need another trick in order to drive this, to detect this very small effect. And in fact, what people do is usually build an haloscope, named after Sikivi, who proposed it in 1983. And the idea is the following. They say, okay, we have these axions. They are very light particles, so there are many of them. They permeate the galaxy. So they behave, let's say, like a classical field oscillating at a certain frequency, which is equal to the axion mass. So basically, what we need to do is to build a radio. So we can actually induce some resonant conversion inside a cavity, such that we can increase like the signal-to-noise ratio for this kind of process. And yeah, as I said, the setup is pretty simple. We have a cavity in a strong static magnetic field, and the goal of the game basically is to match the wavelength of the axion with the resonant mode of the cavity. When this happens, then we have a peak in the power. So that means that the axions are depositing power in our cavity. Obviously, the peak is expected to be very small, and detecting this is a challenging, and it's a very interesting challenge of data analysis and optimization procedure. I wish I would be able to talk about that, but of course, like we are running out of time. So what I want just to show you now about this setup is to play the so-called battleship game of the dark matter search, right? Because we are looking for a particle which has a certain mass, we don't know it. Or since we are talking about frequency, we can also talk about frequency. And we have a certain coupling constant. Obviously, we have some constraint here because, for instance, cosmology says, well, I mean, it can be too massive because otherwise it's going to mess up all the cosmological model. So it's better be at left of the line. And the astrophysicists are saying, well, the coupling constant can be too high because otherwise it's going to mess up the way stars cool down. So we have limits on that. And so we are left out with all this region. Basically, we have to search. And in this region, we have indeed a sweet spot. This is our ultimate goal, like what we aim to detect. Because if an axion happens to have the mass and the coupling constant on that line, it means that it could solve the dark matter problem, and it could solve the fundamental physics problem. So that's when it really makes sense to look for an axion. And if you look at the latest constraints on the axions, we see, first of all, that the region is almost unexplored, which is bad. But this is also quite nice because there means a lot of opportunity. And what we see is there are indeed some experiments that are sensitive enough to reach to the sweet spot we aim. However, if we look at this picture, those, by the way, are, of course, the standard haloscopes. So that means that this is a pretty nice technology to exploit in order to search for axion. But as I said, those comes with a price. Because as we can see from this picture, those exclusion limits are indeed very sensitive. But on the other hand, we see that the lines are very narrow, and they are not very spread out. So there's just a very specific frequency range we can look at. And the problem comes from the fact of the way that a cavity works, because basically, once you build your system, this is a cavity, so it has a certain resonant frequencies, which is very hard to tune because you really have to physically change your system. So it is non-trivial. And if you have a resonant cavity, you are limited by the quantum wavelength of the axion. So you are, okay, say, makes sense to make cavity of the order, let's say, 1 gigahertz. But if you want to increase this frequency, that means that you would need to build smaller and smaller cavities. If you build smaller and smaller cavities, that means that your active volume decreases. And if your active volume decreases, the quantity of axions you can get in that volume decreases. And so you are not very sensitive. So how to overcome this problem? There are other systems that can resonate, and those are plasma. Because also we know that plasma has a frequency, and in this sense it can be used to detect axions, because in a plasma we can have an effective mass of a photon, and so that means that it can pretty well convert in axions. The axion can pretty well convert into photons, and so we can use the technology to detect axion. And that's why you can build a plasma, or even better, we can talk about metamaterials. That's why I'm here today. For those of you who don't know what metamaterials are, we are talking about composite materials. So there are materials whose properties are different from the properties of their small constituents. So if we see, for instance, here we have a depiction of an array of rods. Well, like this system behaves differently from a single rod. And its properties depend rather on the geometry. As I said, if we imagine to put some rods in an array, and we put an electromagnetic field in there, well, what happens with the game, the interplay between the inductances among the rods, what happens is that the electromagnetic field behaves like it was in a plasma, with a certain resonant frequency that depends just on the geometry of your system. So that means, on one hand, that you are no more constrained by the volume of your system, so you can build very systems which are very large, but with a very short wavelength. And this is quite easy to tune, because you just change the geometry, and that's it, basically. You also change your resonance, so you change your sensitivity to the axion. That's what we are doing in alpha, which is this experiment that aims to build a detector to look for axion with metamaterial. The concept of metamaterial is not new, but what is new indeed is the application to the axion search. As you can see, for like our first preliminary simulations, we see that a metamaterial, so just an array of rods as seen on the top, behaves like an effective medium. Yeah, this is basically a plasma with a wavelength that is much smaller. And what you can see also here, like the tuning procedure is quite nice, because you just changed the way the rods are arranged, and you can basically change your resonant frequency. And I want you just to see like that the range is pretty important. Like we are going for 8 to 11 gigahertz, which is way broader than the usual range of an axion oscilloscope search, as I will show you in a minute. And so yeah, like this is a first prototype for the Pathfinder we are building in Stockholm. There's a pretty good agreement. We got it from just the theory and the simulation, just basically putting some rods in a square. And we aim to build a detector which is, let's say, sensitive in the range for 10 gigahertz up to roughly 100 in the future implementations. And since the time is quite over, I would just to conclude with the projection for these experiments. As you can see, we project to reach a pretty nice portion of the parameter space for Axions, which is quite not explored. As you can see, is basically as broad as the current constraints, and that can be so sensitive to reach, like the sweet spot we aim to look at, basically. So we are new, we are young, and we are excited to this experiment, and so stay tuned. If you, of course, have any question, you can contact me at any time. There's the website, and there's Jon Goldmundsson who is working at, let's say, the next phase for this prototype. So again, like, it's still work in progress, but we are very excited about that. Thank you.